Okay, so when we are talking about demand, generally we have an idea of some kind of a function of prices, and there could be other things, income and so on. But usually we write a demand, and we might have a linear one. We might have something else, which is nonlinear. So this is one way to describe demand. But in some cases, we don't have the luxury of knowing what these functions are because data are limited, and you just have no way of doing that, because if you wanted to do that, you would need a lot of data to estimate it. So sometimes what we do is we just concentrate on the idea of, so just the response. So this is simply the proportionate response in quantity relative to the proportionate change in price. So we are just interested in knowing if price changes by 1%, what happens to the quantity in terms of percentage change? And does it go down by half a percentage point, by 2, and so on and so on? And that might be easy to work with. So in general, I don't say this in the lecture, but in many cases when you are studying, if somebody hires you as a consultant and they want you to know, okay, what would be the effect of an increase in price? Well, of course, if you had these functions, that would be perfect, but you are not going to have those functions. And if you haven't been studying the industry, you are going to be wanting to get an idea of what the elasticity is. And this is easier to find because people might have studied it before and so on. So in most cases, you settle there. But if you want to estimate a demand function going from here, and you don't have data, but you have only 2 points. One is, you know what the elasticity is, for example, 0.5 in the example. And you need one more thing. You need a point observation. So the point observation is just one observation, knowing what the price is and what the quantity is at a given point in time. So I could say, well, I know from previous studies, the elasticity of demand for water is minus a half. Let's see what the price is this year. And the price this year is, let's say, $3 a kiloliter. Let's say this is 3 a kiloliter. And let's say the quantity is 35. Then can I work out what the demand curve is? So the whole idea of the point expansion is using this limited information and working your way back to a demand function. But then you need to assume whether the demand function is linear or something else. Well, at least we have figured there are 2 forms where you can just combine these 2 points and make a demand curve. So if it's linear, well, a linear demand function is simply given by A plus BP. And because it's a proper demand function, B should be less than 0, because when price increases, quantity should decline. So B is a negative number, we know that. This is linear, and this is natural for most people, whoever it is, whatever science. If you ask someone to write an equation, linear is the one that comes first to mind. It's like a natural number, a natural form. But you can also have something else. You can have a constant elasticity formula. So basically, this is a nonlinear one because the relationship between Q and P is nonlinear, but the relationship between log of Q and log of P is linear, with the coefficient serving what B was serving here as the coefficient, but they are different functional forms. And we can extrapolate the information we have, or we can utilize the information we have to come up with these equations in this limited information environment with one elasticity estimate and one data point. So that's what we are doing. So let's say we want a linear one. Well, if we want a linear one, what do we need? Let me get a new whiteboard. So I have an elasticity of minus 0.5. I have an observed point. I know that when the price was 3, the quantity demanded or bought was 35. And I assume a linear demand curve, which looks like Q equals A plus BP. And I want to figure out this linear demand curve. Well, figuring out this curve means knowing what A is, what B is. That's all you are after. There's only 2 parameters in a linear demand curve, or a linear equation in general. Okay, so how do we go about this? Well, now, if we have a function like this, what's the elasticity? It is going to be what? It's going to be E equals B times P over Q. Or if you want to write this, is simply P over A plus BP. So if that's the case, then If elasticity is minus a half, then what we have is Q over P over Q, and that's going to be 3 over 35. What can I learn from here? Well, if I combine these two things, I just know that B is minus 0.5 times 35 over 3. And that means my B value should be minus 5833, I believe, right? That's what it's going to be. I am closer to finding the demand curve because now I have the B value, but I need to find A. Well, A is simple because now I know B, I have observation for P and also Q, so I can work out what A is. So A is simply Q minus BP. Well, then given my observation of a quantity 35 and a price 3, then I can do this. And if I do that, I am going to find that my A is going to be 52.5. So we have solved the problem. The demand curve is 52.5. That's my A minus 5.833 P. And I can draw this curve. So what I have managed to do is taken a point that was 35 here and 3 here. I had one observation, and I had the idea that elasticity is a minus half, and I have expanded that into a demand curve. What we are doing, we are starting with a point. We know how elasticity relates to the parameters of the linear demand function, so we use that to find the slope, and then we use the quantity and price data we had along with the slope to find the intercept. And then that means we have created a demand curve that we think could represent what we have here. Let me see if this is clear or not clear. How is it? Is that clear?
Yeah, that's a lot clearer to me. I just have a quick question.
Yeah.
So in what circumstances would you already be given the elasticity value and how would you get that?
That's a good question. That's a good question. Where would you find elasticities? So if you think of demand for things, generally we have a good idea of what the elasticity values are likely to be. In general, we understand, for example, if it's basic necessities, the elasticity values will be numerically under 1, like petrol, food, water, and so on, because these are basic necessities. So the elasticity values will not be big because even if the prices change, people won't reduce by a lot or increase by a lot because these are basic necessities. Whereas for other things that are more luxury type and so on, we know the elasticity values are bigger. We say the demand is elastic. That's one thing. So we generally have an idea of where the range, okay? But that doesn't give you an exact value, right?
Yeah.
It doesn't give you an exact value. But what happens is, again, within classes of commodities, the elasticity values are likely to be stable. So if I take the elasticity value for some commodity, and in societies that are similar, like Sydney, Perth, and so on, I am likely to find a lot of similarity between the elasticity values, or even US and Canada, if I look at drinking water demand and so on. So what that means is I could rely on elasticity estimates from other places as a starting point. So the demand curves could be very different because the demand curve is going to be very different. So if this is Perth, which is smaller cities compared to New York or Sydney, which could be out here, but these look different, but the elasticity values might be similar. And that's the idea. The third reason is, in a lot of cases, there will be previous studies even from the same place. They might be old. So I might have an idea that somebody studied demand for water in Perth 25 years ago. They got an elastic estimate of minus 0.4. I know that. Or maybe people didn't think much about water back then, so they were not very responsive to prices, maybe minus 0.2. And if I have to make a decision about what the elastic could be, and if I have no other information, what I might say is, well, okay, let's start here. And what has happened in the last 25 years? Well, we have had education programs in schools. People are aware of water scarcity problems and so on. And water prices have gone up. So we have been educating people. Water prices have gone up. And when prices go up, people are more sensitive to changes in price. So you wouldn't expect this to be same. But you wouldn't expect it to be -1 either, because that's very high. And for water, we know it wouldn't be that high. So what you would say is maybe you could make an educated guess and say it's -0.5 or whatever makes sense. But there is so many ways. The other thing is this doesn't apply to water, but in general, people have been working on what's called general equilibrium models. So if you look at the consultants, like Monash University had a famous model called Orani model from the, I believe, 90s, 80s for Australia. The consultants would have their own models on to respond to advice, for if they request for advice. So if you walk into a consultancy, that's good enough, but to tell you what would happen if the price of petrol went by 20%, well, they have a model. And these are general equilibrium models. They might have 200 sectors, but how do they know what the demand function and supply functions for the 200 sectors are? They don't know that. They use elasticity estimates from different places and construct models. And since they are interested in small changes in prices, they can construct these things. The systems would tell you if the price of oil goes up, what would happen to the different industries in Australia and so on, what would happen to employment. There were some people in the Department of Ag who had a general equilibrium model for Western Australia, for example. So the point, to come back to your question, is it's easier to get elasticity estimates either from others or from previous studies from the same place, or by making educated guesses based on what's known about the market. But the demand curve is much harder to estimate because that depends on a lot more.
Excellent. That makes a lot of sense. Thanks.
You are welcome. Okay, so that's the linear demand function. So we went from a point to a demand curve. But let me ask you a question. Why would I want a demand curve if I know the elastic? Why can't I just stop with the point? So somewhere in the lecture, there is consumer surplus, right? So if you have been asked, well, could you tell us what the welfare loss to consumers would be if we increase price for water from 3 to 6? Well, you need a bigger story. You need a demand curve. So I could work out what the consumer surplus loss is. So the demand curve has a lot more information than the elasticity. The elasticity is just a story about what happens here or around them. So that's the reason. And if you want to build models that work properly, even these models are using the elasticity estimates to work out demand and supply. So that's what they are doing. If you want to find equilibrium prices, you need that. So that's the motivation. You have a better story. You can talk about welfare loss and so on and give better advice. Okay, let's go back. So what happens if instead of a linear demand curve, I now assume what I have is a constant elasticity demand curve. So for a constant elasticity demand curve, well, that means I am assuming Q is equal to K times P to the power of E. And if this is the case, this is a bit simpler because I have only one parameter to worry about. And I can do everything in one step. K is simply Q over PE. And that's going to give me, the K value is 60.62. So my demand curve is done. That's my demand curve. So this is going to be a curved demand curve, not a straight line. So I have done that. And I have two choices. Of course, what will happen is the two demand curves will be similar around here, but as you go further away from the point where you started, they will tell different stories. But if you are worried about small changes in price, then maybe the answers that you get from the two demand curves won't be hugely different. They are both approximations. You don't know what the two stories, but you are making a guess. And that's what you have to do sometimes. You might as well have a story about how you guess rather than letting people guess the way they want in their own heads without explaining how. And this is what's happening here. So that's the point expansion. And in the linear case, it has got a few more steps, but in the constant elasticity, it's a bit shorter.